Welcome to Analog and Digital Electronics class. This is Swathi, working as Assistant Professor in Institute of Aeronautical Engineering in the Department of Electronics and Communication Engineering. In this lecture, we'll discuss about bridge rectifiers. So, as you all know about rectifiers, so the rectifier is a circuit which is used to convert an AC supply into a pulsating or else DC supply. So the rectifiers are basically classified into two types, half-wave rectifier and full-wave rectifier. So half-wave rectifier, so it is a circuit which is showing the half-wave rectifier construction in which only a single diode is used, and half-wave rectifier is a circuit which is used to rectify only half of the half cycle of input AC supply. That means the diode conducts only during the positive half cycle of input AC supply, whereas the input AC supply consists of both positive as well as negative half cycles. So this rectifier is a major part of power supply where we are going to get a constant DC supply which is required by all the electronic appliances in the real-time world. So next, coming to the full wave rectifier. The full wave rectifier, based on the construction, the full wave rectifier is classified into again two types, that is center tap full wave rectifier and bridge full wave rectifier. So the full wave rectifier is a rectified circuit which is used to rectify both positive and negative half cycle of input AC signal, and hence it is called as full wave rectifier. Whereas half wave rectifier is used to rectify only the positive half cycle of input AC supply, whereas the negative half cycle is removed. So this is the circuit which is showing the construction of center tapped full wave rectifier. Center tapped full wave rectifier. So center tapped full wave rectifier, we are dividing the secondary winding into two halves, and which increases the peak inverse voltage rating of the diode to 2 VM. So this is a major drawback of center tap full wave rectifier, whereas the efficiency is improved when compared with the half wave rectifier, that is 81.2%, and even the transformer utilization factor is improved and the ripple factor is reduced. But the major drawback of center tap full wave rectifier is the peak inverse voltage rating of the diode is high, which is equals to 2 VM, whereas the peak inverse voltage rating of the half wave rectifier is VM, where VM is the maximum voltage of the AC supply at the secondary winding of the transformer. That as we have a drawback, that is the major drawback is peak inverse voltage is doubled, which increases the size of the diode, and hence obviously the cost of the rectifier will also be increased as we are using center tapping. So these drawbacks are avoided. That means we will be trying to overcome the drawback of a center tap full wave rectifier in a bridge rectifier. So bridge rectifier is also a full wave rectifier which is used to rectify both positive and negative half cycle of input AC supply, and hence the number of ripples or else unwanted components present in the rectifier output are reduced and the efficiency will be improved. So here the bridge rectifier circuit diagram is shown here. So in the major differences between bridge rectifier and center tap full wave rectifier is we are not having any tapping in the secondary winding, where we have a center tapping in the center tap full wave rectifier. That is why it is named as center tapped full wave rectifier, where in the center tap full wave rectifier we are using two diodes, two normal PN junction diodes, and in half wave rectifier we are using only a single PN junction diode. Coming to the bridge rectifier, we will be using 4 diodes connected in a bridge-like structure at the secondary winding of the transformer. So this is the structure of bridge rectifier. let us see the circuit diagram of bridge rectifier in detail. So here, to the secondary winding of the transformer, the type of transformer we use here is step down transformer in order to reduce the voltage, that is input AC voltage, which is of 230 volts and 50 hertz, to some lesser voltage. We are using secondary step down transformer. So this is the secondary winding. So we can have a clear circuit diagram of a bridge full wave rectifier like this. So we have primary winding, so which is having more number of turns when compared to the secondary winding, because we are using a step down transformer. So this is primary winding of the transformer. So where we are going to get 230 volts and 50 hertz AC supply in the primary winding. And as we are using step down, this 230 volts will be cut down to our required voltage level. So in the secondary winding, we have 4 diodes which are connected in bridge like structure. Like this. So these are this is the primary step down transformer, and we in the secondary winding of this step down transformer, we have 4 diodes which are connected in bridge like structure. So here the diodes are connected like this. This is D1 and this is D2. Now coming to D3 and next D4. These are the 4 diodes which are connected in bridge like structure, and we have a load resistor which is connected in between. This is, let us consider this as point A, point B, and this is point C and point D, and this is a load resistor across which we will be calculating the output voltage, which is the DC output voltage. DC output voltage is measured across the load resistor. So this is the structure of the diode, and the numbering of the diode, if you see D1, D2, D3, D4, that means the numbering of the diode is given in an anti-clockwise direction, D1, D2, D3, D4. And here this is the complete circuit diagram of a bridge rectifier which uses 4 diodes. Now here, as all the 4 diodes are connected in bridge configuration, so this rectifier is called as bridge rectifier. So this is also a full wave rectifier which is used to rectify both the positive and negative half cycle of AC supply, and hence, as all the diodes are connected in bridge configuration, so this circuit is called as bridge full wave rectifier. This circuit is called as bridge full wave rectifier. So this is about the rectified circuit diagram. So here, now let us discuss the operation of bridge full wave rectifier. So anyhow, we will be getting in the secondary winding also, we will be getting the AC supply. We will be getting AC supply which is having both the positive half cycle and negative half cycle, but only the difference from the primary winding to the secondary winding is, in the primary we have highest voltage which is of 230 volts, whereas in the secondary it will be cut down to our required voltage, that is either 5 volts, 9 volts, 12 volts or 13 volts. Depending on our requirement, we will be choosing the turns ratio. Based on the turns ratio, the voltage will be cut down and it will be given, it will be taken at the secondary winding of the transformer. So now let us see the operation of this one. What happens during the positive half cycle and what happens during the negative half cycle, and how the bridge rectifier rectifies both the positive as well as negative half cycle of input AC supply. So here, as we all know that During the positive half cycle, this point A becomes positive and point B becomes negative. That means the point A of the secondary winding becomes positive when compared with the point B of the secondary winding. That means I can say that during the positive half cycle, point A is at more positive potential, whereas point B is at more negative potential. And during the negative half cycle, point A will be at more negative potential and point B will be at more positive potential. So let us remember this point. And now let us analyze the operation of this bridge rectifier. So at the secondary winding, as we are getting the sinusoidal input, which is having positive half cycle and negative half cycle. So now let us analyze the operation of this bridge rectifier during the positive half cycle. What happens during the positive half cycle? So during the positive half cycle of input, as I said that point A becomes more positive, whereas point B becomes more negative. So now let us analyze the operation of the circuit. As a diode D2, whose cathode is connected to point A, where point A is at more positive potential, this makes the diode D2 reverse biased, because we are connecting, or else the cathode of diode D2 is applied with more positive potential, which makes the diode D2 reverse biased, and hence this will be off, or else we can see that diode D2 is open circuited. Now let us see the diode D1, whose anode is connected to point A, where point A is at more positive potential during the positive half cycle, which makes the diode D1 forward biased. Forward biased means this diode will be on and hence it acts as a short circuit. Now coming to the lower diodes D3 and D4. So the point B is at negative potential during the positive half cycle of input supply. So as the cathode of diode D3 is connected to point B, which is at more negative potential, which makes the diode D3 forward biased. And coming to the diode D4's anode is connected to point B, where point B is at more negative potential, which makes the diode D4 reverse biased, because we are applying negative voltage to the positive terminal. As you all know that anode is a positive terminal, so we are applying negative voltage to the positive terminal of the diode, which makes the diode D4 reverse biased. Means what? Here during the positive half cycle, we can see that diode D1 and D3 are forward biased, and diode D2 and D4 are reverse biased. Reverse biased, when a diode is forward biased, it acts as a short circuit. When the diode is reverse biased, it acts as open circuit. Open circuit means it offers very high resistance for the current to flow, and hence as the resistance is more, no current can flow through the diode D2 and D4. Now if you observe, so as you all know that current always starts from positive terminal. So the direction of current flow is as shown in the figure here with the arrow marks. So it starts from point A, and as the diode D2 is off, which offers very high resistance, infinite resistance, as it is open circuited, no current flows through diode D2 because it is reverse biased and it is open circuit. So now the current will flow from diode D1, which is short circuited, and through point D and through load resistor. Why it is going through the load resistor? Why it is not entering into the D4? Because D4 is also open circuited, and hence there is no path for the current to flow here because it offers very high resistance, and hence the current flows through the load resistor. And the diode D3, as the diode D3 is on, and the current will be flowing through the diode D3 also, and through D3 and to the transformer secondary winding, the other end of the transformer secondary winding. So that is through point B, and it will be repeated like this. So that means during the positive half cycle of input voltage, input AC supply, as a diode D1 and D3 are forward biased, those are short circuited, and diode D2 and D4 are reverse biased, and hence current starts flowing through the load resistor from point A through diode D1, which is on, through the load resistor, and through the diode D3, which is also on, and through the point B of the transformer secondary winding. So here, in this case, the current through the load resistor is in the direction from point D to point C. Point D to point C. And if you see this here, all these components, that is diode D1, load resistor, diode D3, are all connected in series, and hence the same current flows through them. So if you observe the connection here, all are said to be connected in series, and hence same current flows through the diode D1, load resistor, and D3. So as these two diodes are forward biased, it offers some internal forward resistance, which is represented with RF. This one also offers some internal forward resistance. So now this is the current. As the input voltage is varying sinusoidally, the current flowing through the load resistor will also vary sinusoidally. So let us consider this as I1. So this is the current I1 flowing through the load resistor when during the positive half cycle of input voltage, which results in positive half cycle of current across a load resistor. As the current is I1 is varying sinusoidally with respect to time, so the output voltage will also vary with respect to time sinusoidally. So that means V out will also have a positive half cycle of voltage across the load resistor. So this is I1 here. And now this happens due to the positive half cycle of input, in which D1 and D3 are said to be on and D2 and D4 are said to be off. So this is the operation of this bridge rectifier during the positive half cycle of input voltage. During the positive half cycle of input voltage. Now coming to the negative half cycle. As I already told you that during the negative half cycle, the point A of the secondary winding becomes negative, and point B of the secondary winding becomes positive. So as point A is negative, so now this point A is at more negative potential when compared to the point B. So if you observe the diode connections, there is no change, only the cycle of the input is changed. So due to that, so here as point A is at more negative potential, so the diode D1 whose anode is connected to point A, which is at more negative potential, this diode D1 gets reverse biased. And diode D2, as diode D2's cathode is connected to more negative potential, this diode D2 is forward biased. And coming to diode D3 and D4, so as I said you that point B is at positive potential, which makes the diode D4 forward biased because diode D4's anode is connected to point B. That means we are applying more positive potential to the anode terminal, which is positive terminal of the diode, which makes the diode D4 forward biased. And what about the diode D3? Diode D3's cathode is connected to point B, where point B is at more positive potential, which makes the diode D2 reverse biased. So now the diode D3 is reverse biased. So I have shown that the diodes which are reverse biased and open circuited with light color, whereas diodes which are forward biased and short circuited with dark red color. So now in this case, during the negative half cycle of input AC supply, diode D2 and D4 are forward biased, and hence these are short circuited. Or else we can also say that these are on. And now this offers some internal forward resistance RF, very small, negligible forward resistance. And diode D1 and D3 are reverse biased, and hence these are open circuit. and hence these are open circuited. Okay, so here these offers infinite reverse resistance, and hence these are said to be open circuit. Now what happens? So as I told you that always the current starts from positive terminal. So it starts from point B of the secondary winding and through the diode diode D4 which is on, whereas diode D3 is off and hence it offers infinite resistance and hence no current can flow through the diode D3 which is open circuited. So current flows through diode D4 which is on and through the load resistor. Why it is not flowing through the diode D1? Which is because it is also reverse bias and offers infinite resistance and hence no current can flow through this diode D1. So now only there is one path, that is for the current to flow through the load resistor RL. So point B through diode D4 through load resistor RL and through diode D2 which is forward bias and to point A of the secondary winding of the transformer. So here this is the direction of current flow through the load resistor during the negative half cycle of input AC supply. So if you observe the direction of current which is flowing through the load resistor, it is also in the same direction which has happened during the positive half cycle. So during the positive half cycle, the current was flowing through the load resistor from point D to point C. So during the negative half cycle also, the current is flowing in the same direction through the load resistor, that is from point D to point C. So as the current direction is same, so the current through the load resistor will have only positive half cycle. So that means here we have I2, so which is during the negative half cycle of input. So here this is my input signal. So this is Vs. Okay. And here during the positive half cycle, so I'm just considering during the negative half cycle. So as the current is the current direction is same in both the cases during positive and negative half cycle. So we will also have the current I2 only a positive half cycle. We don't have any negative half cycle because in both the cases the current is flowing in the same direction, that is from point D to point C. So this is I2 and here IL is considered to be I1 plus I2, where I1 is the current flowing through the load resistor during the positive half cycle of input AC supply, where I2 is the current flowing through the load resistor during the negative half cycle of input AC supply. So in this case I1, so this D1 and D3 are on, whereas D2 and D4 are off. Whereas in this case the reverse happens, the reverse operation happens, that is D2 and D4 are on and D1 and D3 are off. So as in both the cases, the current can flow through the load resistor, that too in the same direction. So we have only positive half cycles of a positive half cycle of current through the load resistor during both positive and negative half cycles. As the current is having only positive half cycle, the output voltage across the load resistor will also have only positive half cycle. So here this is the direction of current flowing through the load resistor during the negative half cycle of input voltage. Now here these are the waveforms. So AC input, this is the first waveform. This is nothing but AC input, which is Vs, which we can write it as Vm sin omega t, which is having both positive and negative half cycle. This is from 0 to pi, pi to 2 pi, 3 pi, and this repeats 4 pi, 5 pi, 6 pi, and so on. On x-axis, we will be taking omega t. So this is AC input, and here these are the currents. Let us consider this as I1. So this I1 current flows only due to the diodes D1 and D3 which are on. And this is a current flowing through the load resistor during the negative half cycle of input voltage. So, and in this case, the current flows through the load resistor due to the diodes D2 and D4 which are on. And in this case, D1, D3 are off. D1, D3 are off. Whereas in this case, D2 and D4 are off. So these are the currents, two currents I1 and I2 that are flowing through the load resistor, that too in the same direction, and hence this is these are the currents here. Now the total load current IL is considered to be I1 plus I2. I1 plus I2. So which is nothing but the summation of these two waveforms, I1 and I2, which have only positive half cycles of input. So next, as a load current that is flowing through the load resistor is varying sinusoidally with respect to time. So the output voltage across the load resistor, as a current is varying sinusoidally, obviously the voltage will be varying sinusoidally. So this is the output voltage measured across the load resistor. So this is V out, 0, pi, 2 pi, 3 pi, 4 pi. So these are the waveforms of bridge rectifier. So only the thing that you have to remember here is, here in this case, D1, D3 are on and D2, D4 are off. Whereas in this one, D2, D4 are on, D1, D3 are off. So this is the operation of bridge rectifier and its waveforms. So now let us go for the mathematical analysis of bridge rectifier. So if you observe the waveforms, output waveforms of bridge rectifier, these are identical to the output waveforms of full wave rectifier. Output waveforms of full wave rectifier, that is center tap full wave rectifier, where the center tap full wave rectifier was also having only positive half cycles of output. So this is V out or else DC output measured across a load resistor in case of center tap full wave rectifier. Center tap full wave rectifier. Right. So if you observe them, so if you compare this bridge rectifier output and center tap full wave rectifier output, there is no difference. Both are identical. Both are identical. So that is why I can see that the mathematical analysis which we have done for the full wave rectifier is also applicable for center tap full wave rectifier, is also applicable for the bridge rectifier. Is also applicable for bridge rectifier. So that is IDC. So that means the average value of current through the load resistor is given by 1 by pi integral 0 to pi Im sine omega t. If you find out this integration and substitute the limits, you will be getting the value of IDC as 2 Im by pi. Similarly, VDC, we will also get it as 2 Vm by pi. But only the difference here is, so here, either of the case, either during the positive half cycle or during the negative half cycle, two diodes are on, which are connected in series. And hence, if I show this, I can draw this like this. So as a, just a second. So I'm just considering the secondary winding. So as this is diode D1, diode D2, this is during the negative half cycle. So this is RF, let us consider. Consider all the diodes are identical. That means it offers same forward resistance. Okay. And next we have a load resistance RL. So as I told you that all these components are connected in series. All these components are connected in series. So this is the forward resistance offered by the another diode, which is D4. And if you let us consider, if you have some internal resistance to the secondary winding of the transformer. That is, let us indicate that one with RS. And what is the current flowing here? The current flowing is the same current is flowing, that is I1 or I2, or else let us consider IL. So as all these are connected in series, so I can say that IM is equals to, we need to consider the forward resistance of the diode forward resistance of the two diodes which are on. Okay, so IM is equals to VM by, generally we have VM by RF plus RL in case of center tap full wave rectifier. But here in this bridge rectifier, during either positive half cycle or negative half cycle, two diodes are on, and hence two diodes will offer forward resistance. We need to consider the forward resistance offered by the two diodes into effect. So that is VM by RS, which is the internal resistance of the secondary winding, plus 2 into RF plus RL. As I told you that same current flows through the all the elements connected in series. So IM is equals to VM by RS plus 2RF plus RL. So that means we need to observe that there is only one difference from the center tap full wave rectifier to the bridge rectifier. Whereas in center tap full wave rectifier, only one diode conducts. We have to consider RF. That is the forward resistance of the diode which is on at that particular moment. Whereas in this bridge rectifier, during positive half cycle and negative half cycle, both the diodes, two diodes are conducting. So we need to consider the forward resistance offered by the two diodes into effect. So that is why IM is equals to 2 VM by RS plus 2 into RF plus RL. So that means blindly we can say that wherever you find RF, we need to place 2 into RF in the analysis of center tap full wave rectifier in order to obtain the analysis of bridge rectifier. So that means what we have seen, IDC is equals to 2 IM by pi. Similarly, VDC is equals to 2 VM by pi. Or else we can also say that VDC is equals to IDC into RL. Okay, where IDC is equals to 2 IM by pi into RL, where IM we can write it as 2 by pi into RL into IM is VM by RF, 2 into RF plus RS plus RL. Anyhow, forward resistance is very less. So, and even the internal resistance of secondary winding of the transformer is also very less. So, if you consider 2 into RF plus RS is very much less than RL, I can neglect this. So, in that case, VDC is equals to 2 by pi into RL into VM by RL. If I neglect this, I can get only RL in the denominator. This one get cancelled. So VDC is equals to 2 VM by pi. So IDC is 2 IM by pi and VDC is also equals to 2 VM by pi, which is same as that means the average value of output voltage and average value of output current is equals to 2 VM by pi and 2 IM by pi respectively. This is same as that center tap full wave rectifier. Only the difference here is during either of the half cycle, we need to consider the forward resistance offered by the two diodes, because at a time two diodes are conducting and hence we need to consider the forward resistance offered by the two diodes. Okay, and similarly IRMS is equals to, so these are all same as that center tap full wave rectifier, because the output waveform of center tap full wave rectifier and bridge rectifier are identical. Only the thing, two diodes conduct at a time in the bridge rectifier. So next, similarly VRMS is also equals to VM by root 2, and even the efficiency, percentage of efficiency is 81.2% because there is no difference in the output power and output voltage and output current. These are same, and only the thing that is PAC will be varying, that is IRMS square into RS plus 2 into RF plus RL. 2 into RF plus RL. So this is the PAC value. So PAC value will be varying. So we need to consider two resistors which are connected in series, that is two diodes which are connected in series, and they are offering some forward resistance RF. So PAC, and even the ripple factor is same as that is 0.482 because there is no change in the values of VDC and VRMS. And similarly, okay, now coming to the transformer utilization factor. So the transformer utilization factor. So we have calculated the transformer utilization factor for center tap full wave rectifier by taking the average of transformer utilization factor of primary and secondary. But here that was happened because we were having a center tapping. We were having a tapping at the center of the secondary winding of the transformer. But here, as we don't have any center tapping here, simply if you calculate the transformer utilization factor of the secondary that we have already calculated, that is transformer utilization factor is equal to the equals to the transformer utilization factor of secondary. Transformer utilization factor of secondary winding. So that is given by PDC divided by PAC rated. So PDC is nothing but VDC into IDC divided by PAC is nothing but VRMS into IRMS. So that is 2 Vm by pi into 2 Im by pi divided by RMS is Vm by root 2 into Im by root 2. So Vm, Im get cancelled. So what we will be getting 8 by pi square, which is equals to 0.812%. So the transformer utilization factor of this bridge rectifier is equals to 0.812. So whereas the transformer utilization factor of center tap full wave rectifier was 0.693. So it is improved further. So this is the major advantage we can observe in the bridge rectifier over the center tap full wave rectifier. And one more thing, so the remaining all the factors are same, that is form factor, peak factor are all same. Form factor, peak factor are all the same things. So form factor is 1.11 and the peak factor is 1.414. So these are all same as the center tap full wave rectifier. And one more difference that we can observe here is peak inverse voltage. So the peak inverse voltage, what happens to the peak inverse voltage? So in case of center tap full wave rectifier, the peak inverse voltage was 2 Vm. That was a drawback. So which we are overcoming here. Why? Because so here this is a bridge rectifier circuit. This is a bridge rectifier circuit in which we don't find any tapping at the center of the secondary winding. So that means secondary winding is not divided. We are just connecting 4 diodes to the secondary winding of the transformer in bridge configuration. So that is why if either of the that means during positive half cycle or negative half cycle, 2 diodes are conducting and 2 diodes are non-conducting. So as a whole, we are going to get Vm voltage at the secondary winding. So which will be dropped across the diodes D2 and D4 in this case. Similarly, in the previous case, D2, D1 and D3. That means the peak inverse voltage rating will be same as the half wave rectifier, as we don't have any center tapping at the secondary winding. So the voltage is not getting divided into equal parts. So we will be getting Vm volts of voltage at the secondary winding, which is only going to be dropped across the diode which are reverse biased. As you all know, the peak inverse voltage is the maximum reverse voltage that a diode can withstand without any damage. So the diode can withstand maximum voltage, that is Vm, in case of bridge rectifier, and hence the peak inverse voltage of a diode in bridge rectifier is Vm. So we have reduced the peak inverse voltage when compared to the center tap full wave rectifier without disturbing the efficiency, ripple factor, and remaining all the factors. Even the transformer utilization factor is also improved. So that is why this is the circuit which is majorly used in the designing of regulated power supplies. So now this is about the mathematical analysis, so that you can observe the difference in the maximum current flowing through the load resistor, that is Im is equals to Vm by Rs plus 2Rf into 2Rf plus R. And one more difference, transformer utilization factor is improved and peak inverse voltage is reduced. So this is about the mathematical analysis of bridge rectifier. As all the analysis is same, we are not discussing it. Just remember that. Now coming to the advantages of bridge rectifier. So efficiency is improved, that is 81.2, which is double the efficiency of half wave rectifier. And the ripple factor is reduced, which is up to 0.482. And frequency is also improved here. So because we have 2 cycles, so the frequency will be improved here. Okay. So transformer utilization factor is more when compared to the center tap full wave rectifier, whose value is 0.812. And no center tapping is required, and hence cost will also be reduced when compared to the center tap full wave rectifier. And peak inverse voltage is half that of the center tap full wave rectifier. Now coming to the disadvantage, these are all the advantages that we can observe in the bridge rectifier. Coming to the disadvantage here, so it uses 4 diodes, and those are also connected in bridge configuration. So the circuit is little complex and even costlier. So this is a major drawback that we can observe in the bridge rectifier. As we are using 4 diodes that are connected in bridge configuration, the circuit is somewhat complex and it is also costlier. And one more major drawback that we can observe here is, in either of the half cycles, 2 diodes are on. And one more thing, we are using 4 diodes, and in either of the half cycle, that is either during the positive half cycle and during the negative half cycle, 2 diodes are getting on, and hence there will be some resistance offered by the diode, which is indicated by 2 into Rf, as 2 diodes are on at a time, that is either during negative half cycle or positive half cycle, and hence there as the 2 diodes are on, there is some additional voltage drop across the diodes, which further reduces the output voltage. So that means, in short, I want to say here it is, the circuit is complex and somewhat costlier, as we are using 4 diodes that are connected in bridge configuration. And one more drawback is output voltage is reduced, as 2 diodes are becoming on during either positive or negative half cycle of input voltage. Now coming to the comparison of rectifiers. So as we have we know that there are 3 types of rectifiers: half wave rectifier, full wave rectifier, and bridge rectifier. So these are the differences that are shown, that we can observe in the circuit configuration of half wave rectifier, full wave rectifier, center tap full wave rectifier, and bridge rectifier. In half wave rectifier, we don't have any center tapping, only single diode is used. Whereas in center tap full wave rectifier, two diodes are used and a tapping is used at the center of the secondary winding. Whereas in case of bridge rectifier, there is no tapping at the center of the secondary winding, but four diodes are used here which are connected in bridge configuration. So this is the difference in the circuit diagram. Now coming to the mathematical, that means the differences among the half wave rectifier, bridge rectifier and center tap full wave rectifier according to the mathematical analysis. So the number of diodes used in half wave rectifier is 1, whereas in center tap full wave rectifier it is 2, and in bridge rectifier it is 4. Coming to the average current, that is the DC output current flowing through the load resistor, is given by Im by pi in case of half wave rectifier, and in case of bridge and full wave rectifier it is same, that is 2 Im by pi and 2 Im by pi. Coming to the RMS current flowing through the load resistor, which is given by Vm by pi in case of half wave rectifier, 2 Vm by pi or ESM by pi, whatever notation you want to use, you can use, and 2 ESM by pi. There is no difference in full wave, center tap full wave rectifier and bridge rectifier. And DC output power and DC output voltage is Vm by pi, 2 Vm by pi and 2 Vm by pi. And RMS current Im by 2, Im by root 2 and Im by 2 in half wave rectifier, whereas Im by root 2 in both center tap full wave rectifier and bridge rectifier. And DC output power is Im square by RL into pi square in case of half wave rectifier, 4 by pi square into Im square into RL in case of full wave rectifier, and bridge rectifier also the same thing. Coming to the AC input power, Im square into RL plus RF plus RS divided by 4, because we already know that PAC is equals to IRMS square into RS plus RF plus RL, where IRMS value is Im by 2 in case of half wave rectifier, and whereas IRMS is equals to Im by root 2 in case of full wave rectifier, that is either bridge rectifier or center tap full wave rectifier. So that is why Im square by 4 into RL plus RF plus RS, where RF and RS are the internal resistances of diode and secondary winding of the transformer. This by 2, whereas we have 2 RF because 2 diodes are on in case of bridge rectifier during either of the half cycle. So that is a difference that you can observe. Now coming to the efficiency of half wave rectifier is 40.6, whereas center tap full wave rectifier it is 81.2, and for bridge rectifier also it is 81.2. And maximum load current, that is Vm by Rs plus Rf into RL for half wave rectifier, and for bridge rectifier, full wave rectifier, that is center tap full wave rectifier, it is Vm by Rs plus Rf plus RL, and in case of bridge rectifier, Vm by Rs plus 2 Rf plus RL, because 2 diodes are on at a time. And peak inverse voltage of the diode is Vm in case of half wave rectifier, and 2 Vm in case of center tap full wave rectifier, and again Vm in case of bridge rectifier. And the ripple frequency is 50 Hz, because in case of half wave rectifier, negative half cycle got removed. So that is why it is half of the input frequency, that is 50 Hz, whereas in this case, double the input frequency, that is 2 into 50, it is 100. And coming to the transformer utilization factor, which is very less, and that is 0.287 in case of half wave rectifier. And in case of center tap full wave rectifier, it is somewhat larger, that is 0.693. And it is improved further in bridge rectifier, which is 0.812. So this is about the comparison of bridge rectifier, that is based on the construction and also the mathematical analysis. We have compared the various types of rectifiers, that is half wave rectifier, center tap full wave rectifier and bridge rectifier. I hope it is clear to everyone. I'm closing the session. Thank you, one and all.
Like, share, and subscribe. Hit the bell icon for more updates.